Good afternoon to everyone. I welcome all of you to the 64th lecture in the lecture series in nonlinear dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. Today, we have a speaker from Spain, and it is my pleasure to introduce you the speaker, Professor David Gomez Ullate. Professor Ullate obtained his PhD in physics from Universidad de Complutense de Madrid, Spain in the year 2001. He carried out postdoctoral studies at a well-known mathematical institute, namely Center for Mathematical Research, Montreal, Canada, for an year. He came back to Europe and carried out another postdoctoral studies at Bologna, Italy, for an year. He then moved to Spain back and continued his research for a couple of years at Universitat Politécnica de Catalunya and another couple of years at Universidad de Complutense de Madrid. He has been appointed as Associate Professor of Applied Mathematics in the same university in the year 2013. After 2018, he has been appointed as Distinguished Researcher and Director of UCA Data Lab, University of Cadiz. Professor Ullate's research interests span a wide range of topics, ranging from mathematical physics and approximation theory to applied machine learning and data science. His major contribution is the theory of exceptional orthogonal polynomials, which has earned him international recognition, expressed as plenary talks in the main conferences of the field, and invited seminars at Cambridge, Edinburgh, Stockholm, Copenhagen, and Rome, among others. Interestingly, Professor Ullate is also working with industry. For the past 10 years or so, he has specialized in knowledge transfer of mathematics to industry. He is currently president of the Knowledge Transfer Commission of the Royal Spanish Mathematical Society and a member of its governing board. In 2016, he received a Leonardo Fellowship Scholarship from BBVA Foundation for a project on credit card fraud detection. He has coordinated 8 knowledge transfer contracts with industry in the financial, fisheries, biomedical, and aeronautical sectors. He is currently leading Smart Shipping, a project on optimization of shipping routes based on oceanographic data and forecast that aims to have a considerable impact on decarbonization of the maritime sector. Together with his former PhD students and postdocs, Professor Gomez Ullate founded and serves as scientific advisor of the technological startup Komoroi. I read many of his works related with exceptional orthogonal polynomials. Inspired by his works when I was in Madrid in the year 2012, almost 10 years ago, I paid a visit to him and presented a seminar in his department. It was a nice experience to visit one of the oldest universities of the world and to interact with him. Today, I'm happy to hear his lecture. With this short introduction, now I invite Professor Ullate to deliver his lecture. Over to you, Professor.
Thank you very much, Professor Santilvalan. It's really a pleasure to be with all of you today. You were very far, and I don't get really to see your faces. I hope that this virtual interaction will, at least in some sense, convey some of the information and the passion that I want to transmit to you. So I'm going to share my screen now, and I will start presenting some slides. Let's see. So I guess you see my screen now.
Yeah.
Okay. Now why is this not working? Okay, for some reason now this is not working. Let me see. Okay. All right. So now you're seeing my slides, I guess.
Yes.
I don't see any of you. I'm talking to a screen, so
yes.
It's a little bit funny. I hope not to bore you too much. Now, if there are any questions and you want to stop me, please do. I mean, I don't know. Maybe if some of you are watching the panel, raise your hand, speak into the microphone. Don't save your questions until the end if you have something that you want to ask. So please do interrupt me. All right. So I want to start my talk with some objects that you know very, very well, at least because probably they pertain to some of the basic courses in physics and mathematics. And they relate to these objects called classical orthogonal polynomials. Okay. So classical orthogonal polynomials, for the mathematicians, you can think of them as the basis of a Hilbert space composed of very simple functions, namely polynomials. If you're a physicist, then you've probably seen them appear in many, many applications. And the reason why is because classical orthogonal polynomials are also solutions of a second-order differential equation. And most interesting equations in physics, mechanics, and in quantum mechanics, they are second-order equations. So that's the reason why these things appear. So just to give you, in mathematics, they are also used for many other topics, like numerical analysis, interpolation, approximation. They have very good properties, okay? Now, the two examples that I want to give you that are probably known to all of you are spherical harmonics, which all of you have studied quantum mechanics. I guess you've encountered spherical harmonics when you separate variables of the Laplacian in spherical polar coordinates. Well, spherical harmonics are a special case of Jacobi polynomials. Okay, they're classical polynomials. Zernike polynomials, I don't see you, but I think that there's around 20 to 30 of you in the audience. Maybe some of you are carrying glasses. Well, if you are carrying a set of glasses, you are carrying a set of Zernike polynomials every day with you. And the reason is that Zernike polynomials, which are again a special case of Jacobi polynomials, which are orthogonal on the unit disk, they are used in the ophthalmic industry to approximate the surface of a lens. So every time that you have glasses and you go to the optician and you give them the parameters to design a given lens, you're using a basis of classical orthogonal polynomials. So they are really very useful. They appear in many, many applications. And normally people study them in great detail. Now, from a mathematical point of view, let me just give you a characterization of orthogonal polynomials, classical orthogonal polynomials. And I mentioned they are characterized as the solution, if you want, of an eigenvalue equation, which is a second-order differential equation. So here the f's are these classical orthogonal polynomials that satisfy the differential equation q f double prime plus l f prime plus lambda f equals 0, okay? Where q and l are normally polynomials of degree 2 and 1, okay? Now, these orthogonal polynomials, they normally orthogonal with respect to a given weight, and the weight has the form that you're seeing on the slide. So if the weight has 1 minus x to the alpha, 1 plus x to the alpha, this is the Jacobi weight. Hermite weight is just the Gaussian factor, and Hermite polynomials are orthogonal on the whole real line, whereas Laguerre polynomials are orthogonal on the half line, and the weight is the one that you see there. Incidentally, these things are also very important for statistics. Okay, so orthogonal polynomials are related to the main statistical distributions, like the beta distribution and the gamma distribution, and so on. Okay, so they are the kernel of many statistical functions too. So they are very, very important objects in pretty much all of mathematics and a lot of physics. So the story that I want to tell you today is that we can actually go beyond classical polynomials while preserving many of their properties. And these are precisely exceptional polynomials. So I'm going to tell you a little bit the motivation on how we discovered these things back in 2009, 2010, more or less, so already more than 10 years ago. And the story starts with this person, which is called Solomon Bochner, who was a very prolific mathematician. He had some of his students who were very well-known mathematicians like Helgason, Calabi, which you probably know from the Calabi-Yau varieties in theoretical physics. Dick Askey is one of the father of the modern theory of orthogonal polynomials. He has his name in the Askey scheme. So this person had a lot of contributions, but today we want to talk about the paper that he wrote when he was young. He was still in the University of Munich, 1929. And the paper is called Über Sturm-Liouville'sche Polynomsysteme, which means on a polynomial system of Sturm-Liouville type. Okay, so Sturm-Liouville type, in case you haven't heard about this, and if you're physicists, you don't need to hear the word Sturm-Liouville, you can think of Sturm-Liouville as being like a self-adjoint operator on a Hilbert space. That's essentially the same. Okay, so you have a second-order differential operator with normally boundary conditions such that it defines a spectral problem. Okay. Now, what Bochner did in this paper, it's a very short paper, just 6 pages, is that if you have a differential equation of the form that you see there on number 1, which is the one that we've been looking at, and you demand that there's a sequence of eigenvalues, lambda 0, lambda 1, all the way to lambda n, and a sequence of polynomials such that there is a polynomial eigenfunction for each and every degree. So if you demand that, then you conclude that it's a very simple calculation to describe the set of all Sturm-Liouville polynomial system. And this is what he did in this paper. Okay, and it's a classical paper. It's been very highly cited, and look like the word "all" is emphasized in the original paper. So he really believed that he's having the set of all Sturm-Liouville polynomial system. Shortly after that, again, another important mathematician, Peter Leski from Austria, he reformulated Bochner's problem into a more modern spectral theoretic language. Okay, and again, it's another paper. It's again written in German, but again, he comes out with a very similar conclusion. He says, we address the claim that the classical orthogonal polynomials are the only orthogonal polynomial solutions of a differential equation of Sturm-Liouville type. Okay, now, this is a characterization result. So normally people, until very recently, they thought that classical orthogonal polynomials of Hermite, Laguerre, and Jacobi are the only solutions that you can have to such a differential equation. Okay. Now, is it really true that these are the only ones? Well, let's see what Bochner theorem actually says. It says, as I said before, that if you have a sequence of polynomials with degree of yn equals n, so you have a sequence of polynomials that contains all degrees, and they satisfy this differential equation, where p, q, and r are in principle arbitrary coefficients, arbitrary functions of x, then it very quickly follows that p, q, and r have to be polynomials. The degree of p has to be at most 2, the degree of q has to be at most 1, and the degree of r is 0, so r is just a constant. Okay, and moreover, up to an affine transformation of the independent variable x, you only have 3 big families, and this depends on whether p has 2 simple roots, so p is degree 2, or p is degree 1, or the degree of p is 0. Okay, and these are the 3 families named after Hermite, Laguerre, and Jacobi that have been known for at least 150 years. Okay, now how can we depart from this scheme? Well,
so Legendre polynomials are not included here?
Legendre polynomials are a special case of Jacobi polynomials. And so are, yeah, so Legendre polynomials are a very special case of Jacobi polynomials when alpha and beta are 0. And Chebyshev polynomials are also, sorry?
Including the associated Legendre polynomials?
Associated Legendre polynomials, they are all special cases of Jacobi. Gegenbauer polynomials, Chebyshev polynomials, they are all special cases.
Okay, okay, thanks.
So normally, if you have polynomials that have a name and that you are acquainted with them, it's mostly the case that they are actually special cases of these 3 families. Okay. Now, the way to depart is very simple. Instead of demanding that there's a polynomial for every degree, just change that and demand that there's a polynomial for every degree, except perhaps for a finite set. Okay, so it's less a stringent condition. You could have certain degrees for which you don't demand that there's such a polynomial. If you relax this assumption, then it no longer follows that p, q, and r have to be polynomials. Now, actually, there could be rational functions. So you are already in a larger family. Okay? But by demanding less, you are enlarging your family. So P, Q, and R could be rational functions. And instead of having the classical polynomials, you have the exceptional polynomials. So this is what exceptional polynomials are. And now I'll give you a definition. And we call them exceptional Hermite, exceptional Laguerre, and exceptional Jacobi, with an X in front of the word. But wait a minute. I mean, I told you this, and I don't see your faces, so I don't know what you're thinking about it, but you should probably think and ask yourself the following question. Look at the eigenvalue equation that I just showed you. And I told you that Q and R are now rational functions, okay? But the y's, the eigenpolynomials, are polynomials. Lambda is a constant. So that means that the right-hand side of this equation is a polynomial. Now, the left-hand side is polynomials and derivative of polynomials multiplied by rational functions. So in general, this is a rational function. Now, how can you have an equality between a rational function and a polynomial? Well, necessarily there have to be cancellations on the left-hand side. Okay, so that rational function needs to be a polynomial. Okay, so some cancellation must happen. But look, this cancellation should happen for every I. And I ranges over an infinite countable set for all natural number except for a finite set. So you have an infinite number of cases where these things, cancellation should happen. And yet, P, Q, and R are fixed. So how is this little miracle happening? Okay, and I challenge you to find an example just by direct inspection to see whether you can find an example of such a P, Q, and R where this property holds. And it's not easy. I mean, if I don't tell you what the trick is, then very likely you won't be able to find an example. Okay, so this is the first question that could be a little bit puzzling. Now, the second question is, now there are missing degrees. If you think about the completeness of this family, is it still possible that the remaining polynomials span the basis of a Hilbert space? Okay, are they a complete family? And this is very important because if you want to approximate functions, you better have that your set of basis functions is complete. Now, if you take Hermite polynomials or Legendre polynomials and you throw away a couple of them, the remaining set is of course not complete. Okay, but in this case it will be, and that's also one of the questions that we asked ourselves at the beginning. All right, definitions. So a second order operator, we call it exceptional if it has polynomial eigenfunctions for all but finitely many degrees. Okay, so you have this eigenvalue equation that holds, and you have an infinite set of polynomials y sub k, but you don't need to have a polynomial for every possible degree. You could have a number of gaps in the degree sequence. Okay, if that holds, then you have an exceptional operator. And to have an exceptional polynomial system, you need to add some extra conditions to make sure that this is a well-defined spectral theoretic problem. Okay, so you have a countable sequence of polynomials, and this forms an exceptional orthogonal polynomial system if, well, the yns are of course the eigenfunctions of an operator t, as I defined above, but define an interval of the real line and a weight function such that you have a well-defined measure where all the moments are defined. Okay, so W is a positive single-valued and integrable weight. All the moments of W are defined, and you have some suitable boundary conditions to ensure that that there is convergence of the scalar products. Okay, so this defines a spectral theoretic problem, and finally, you need to ensure that the polynomials span a basis, they are dense in the weighted Hilbert space. Okay, so if all these conditions are met, then you're speaking of an exceptional orthogonal polynomial system. Let me give you an example of what the simplest such example would be. Okay, because otherwise, if we talk a lot about the definitions and so on, maybe you lose interest on what you're doing. Okay, so I'm going to give you an example. The example is the following. So define your yn, your polynomials, as the Wronskian. Remember, the Wronskian determinant is an object where you write those functions and then you take derivatives of higher order as you go along on the subsequent rows. Okay, that's a Wronskian determinant. So you fix H1 and H2, and H are Hermite polynomials, and you let Hn vary over the remaining set. And the remaining set is that Hn, n could be 0, 3, 4, 5, all the way up to infinity. Now, I don't put 1 and 2, because if I put 1 and 2, you know the Wronskian, when what you put into the Wronskian is linearly dependent, the Wronskian would be 0. It's just a determinant. Okay? So 1 and 2 would give you 0. So I take those from my degree set. Well, this you have to believe, but I could prove it to you, that if you define these polynomials, they satisfy the following eigenvalue equation. And you see, this eigenvalue equation looks a lot like Hermite equation, except that it has that funny extra term, 4x over 1 plus 2x squared. Okay, and this term is new. So if you calculate what are the first few polynomials, you give n equals 0, n equals 3, n equals 4, n equals 5, you get the following polynomials. And look that there are no polynomials of degree 1, and there are no polynomials of degree 2. So the sequence starts with degree 0, and the next one is degree 3. And then 4, 5, all the way to the up. So there's a gap. There's a gap in the degrees. Okay. Well, not a problem. I mean, if that is not a problem for you, that's not a problem for me either. Well, and this you have to believe also, that set, even though it doesn't have any polynomial of degree 1 and degree 2, it's still a basis of the weighted L2 space. And here you have to understand that it's a basis in the L2 sense. So that means that you need an infinite number of polynomials to approximate any square integrable function. Okay, you approximate to an arbitrary degree of accuracy in the L2 norm, but you cannot write it as a finite linear combination. Okay, so it's a basis in the L2 sense of the word. You can also look at these polynomials as the set of all polynomials that satisfy a given condition, and this condition is what you're writing there, that there's a 2 times x times the derivative of p evaluated at 2 certain points is 0. So it's a first order condition at 2 specific points. And that is another way of characterizing the span of all these polynomials. Now the weight, look at the weight. I mean, the weight looks like the usual Hermite weight, which is just the normal distribution, the Gaussian, but it's divided by a polynomial squared. The polynomial is 1 plus 2x squared again. But that weight, if you look at that weight over the reals, it's a perfectly well-defined weight, right? I mean, 1 plus 2x squared is nowhere 0, so it has no poles or anything like that. It's a perfectly well-defined function. It will decay to 0 at plus and minus infinity sufficiently fast. So the weight is perfectly fine. Okay, it satisfies all the requirements. And likewise, the orthogonality relation that you see there, it's also a small modification of your orthogonality relation that you would have for the ordinary Hermite polynomials. Okay.
Excuse me, Professor.
Yes.
So how do you determine this weight function in the usual way, or the weight function, W?
Yes.
How do you determine the weight function?
Yes, the weight function is very easy to determine from the coefficients of the differential equation. So there is a thing called Pearson's equation that tells you that given the differential equation, the weight is automatically determined. So you read it from the coefficients of the differential equation.
Yeah.
There's a formula that involves an integral and an exponential. And
yeah, it's the usual formula, e power p by q, something like that.
Exactly.
Okay.
Yeah, there's nothing magical about the weight. I mean, the weight is just somehow encoded on the differential equation.
Right.
Okay. Now, you do need to make sure that the weight is regular on the interval of orthogonality, and that requires some further restrictions. Okay. So that, of course, you need to do if you want to stay within a regular problem. Okay. So this is just a short introduction. Now, a few years ago, together with my collaborator, Robert Nilsson, in Canada, and María Ángeles García Ferrero, who was a former student of mine, we published this paper in the Journal of Journal of Mathematical Analysis and Applications, where we basically we don't provide a full classification of these objects, but we provide a characterization theorem, which is the following. Okay, the theorem says that if you have an exceptional orthogonal polynomial system, necessarily you can obtain it by applying a finite sequence of Darboux transformations to a classical orthogonal polynomial system. Okay, so no matter what your exceptional orthogonal polynomial system is, if you have one, there should be a sequence of Darboux transformation that starts on a classical system and leads to the system that you have. Okay? And this is very important because it means that we don't need to look elsewhere. This is all that we need to do. So this is like a preliminary result for the full classification. In order to have a full classification, what we need to do is we need to study all the possible Darboux transformations that you can perform on the classical systems. Okay, and I haven't told you yet what a Darboux transformation is. Maybe you know, but I will get to that in a second. So since most of you are physics students, let me try to connect this a little bit with physics. Okay, so in physics, you know, one of the probably the simplest quantum mechanical systems that you know, also in classical, is a harmonic oscillator, and your potential is just x squared. Okay, we throw away all the constants, and that's x squared, and you have a nice parabola, so that's your potential. So a rational extension of the harmonic oscillator means that you are allowed to add a rational function to x squared. Now, the rational functions, you should add it and still preserve certain properties. The first of all is the degree of p is smaller than the degree of q, which means that your perturbation at plus minus infinity goes to 0, which means that your potential, your rational extension, asymptotically at large x, it behaves like the harmonic well. Okay, so if you look at it from a distance, you're just seeing a harmonic well. Now, at small x, you could have all this complicated pattern of peaks and wells, and that's fine. Of course, you should demand that polynomial q does not vanish on the real line, because otherwise you would have a singular potential, and we don't want that. And this is the hardest part. You want to add a p over q such that the Schrödinger equation remains exactly solvable. So you should still be able to compute the whole spectrum and eigenfunctions of Schrödinger equations. And now they will not be Hermite polynomials anymore, times a Gaussian, but they will be exceptional Hermite polynomials. Okay? This is the idea. So these rational extensions of the harmonic oscillator, they've actually been studied by many, many people, and they've been classified. Okay, so it turns out that the only rational extensions, in the way I defined them before, are the ones that you can obtain by applying a finite number of rational Darboux transformations to the harmonic oscillator. And they have the following form. So if you start from the harmonic oscillator, your spectrum, as you know, is an equispaced spectrum. So you have a constant spacing between each energy value. Okay, this you know very well. Well, if you now do this transformation where you add the log of the Wronskian of H1 and H2 with the second derivative, you see the form of the potential develops that little kink. So that's not the harmonic well anymore. And you're making disappear the levels at energy 1 at energy 2. So you have this big gap, and the rest of the spectrum is pretty much the same. And this is precisely the example that I showed you before. Okay, so it's almost like you have the spectrum of the harmonic oscillator, but you're erasing levels. And why stop here? You can continue doing that. So you can do 1, 2, 5, and 6, and then you're making another gap. Okay, and you see the form of the potential keeps changing. Or you can do this other formula where you have 1, 2, 5, 6, 11, 12, 13, and 14, and you're making gaps into your spectrum. And again, asymptotically, it looks like a harmonic well, but near x equals 0, the potential can be very complicated. Okay, and nevertheless, this thing is still exactly solvable, and the eigenfunctions, I will tell you in a second, will be this exceptional Hermite polynomial. Now, maybe you observe that every time I'm adding polynomials into the sequence, I'm doing them in chunks of even length. And there's a reason for that. The reason is that that's the only way to ensure that your Wronskian does not vanish on the real line. Okay, so if your Wronskian vanishes, then when you take the log derivative and the derivative of that, this will blow up, and you don't want that. Okay. So what about the eigenfunctions? If I show you this graph, this is a question for the students in the audience. So what do you think that this function is? Somebody wants to say something? No? It's a familiar function, right? Doesn't it look like this thing? Yeah, it does, right? It looks like this. And this would be the ground state if you have the harmonic oscillator. This looks like a ground state. Well, only that's not the one, okay? That function that I just showed you is, in fact, this function here. And if you look at it, it's a polynomial of degree 4 divided by another polynomial. The Wronskian of Hermite polynomials is a polynomial times e to the minus x squared. Well, I mean, at plus minus infinity, of course, the thing will look like the same. And perhaps the interesting part here is that because the polynomial 4x4 plus 3 does not vanish on the real line, this thing actually looks a lot like the graph that I showed you above. In fact, it is the graph that I showed you above. Okay? If I show you this graph here, what would it look like? Normally, you would be expecting something like this. This would be the first order Hermite polynomial times the Gaussian with just 1 0. Okay? And again, that's not the one. It's a polynomial of degree 7 divided again by a Wronskian and times e to the minus x squared. So it's a polynomial of degree 7 that only has a real 0, which is because it's the null polynomial. And you can continue like this. And if I only showed you the graphs would look exactly as what you would be expecting from what you know in quantum mechanics. So they have the oscillation property, right? I mean, all the zeros interlace and so on and so forth. The graph looks something that you know very well, but the formulas are different. Okay, so the analysis is the same, but the algebra is different, if you want. So let me write all these eigenfunctions here. You see, all of them have the same form. All of them have the form a prefactor times a polynomial, and that's usual in quantum mechanics. So these polynomials are actually the first exceptional Hermite polynomials associated to the sequence 1, 2, 5, 6. And again, as you see that there are jumps in the degree. The orthogonality weight is the one that I showed you before. Is e to the minus x squared divided by the square of a polynomial. And if you plot it, it looks almost like a Gaussian, except with a different type, but it doesn't. It's not there's nothing wrong with the weight. Okay. So if you look at the number of real zeros, and this I showed you on the plots before, the first eigenfunction has no real zeros, as it corresponds to a ground state. The first excited state has 1 real zero, the next one has 2 real zeros, and the last one has 3 real zeros, and so on. So the eigenfunctions have exactly the number of real zeros that you would expect from what you know. And in fact, it has to be that way, because this is a Sturm-Liouville problem, and every Sturm-Liouville problem have the oscillation theorem, satisfies the oscillation theorem. Okay? The eigenfunctions only have simple zeros, and the zeros interlace, and so on. Okay, so there's no way you can escape that, and in fact, it does. But look, I mean, this eigenfunction is a polynomial of degree 11, and it only has 3 real zeros. So what are the extra zeros? Well, if they're not on the real line, they can only be on the complex plane. Okay, and because a polynomial of degree 11 should have 11 zeros, there has to be some extra zeros. So this leads me to the following question, which is, what can we say about the zeros of exceptional polynomials? And we will see that there are two types of zeros. Some zeros that I will call regular, they are exactly the kind of zeros that you know how they behave, because they mimic what the classical polynomials do. So they lie in the support of the measure, they lie in the interval of orthogonality, they are simple, they have the interlacing properties, they follow the same asymptotic as the classical cases. Everything that you know from the zeros of classical polynomials happens for the regular zeros of the exceptional polynomials. Okay, but exceptional polynomials also have another set of zeros that we call exceptional zeros, and they lie outside the support of the measure. So if you're on the Hermite problem, they lie outside the real line. They are in the complex plane. There are as many exceptional zeros as the codimension of the problem. The codimension of the problem is the number of missing degrees in the sequence. Okay, and we also know many things about them, which I don't have time to tell you about how they behave under different asymptotics. Okay, so they accumulate at certain points on the complex plane, but I don't want to get into that. Now, I don't know if you've seen these pictures before, maybe in some drawings by Peter Clarkson, but these complex zeros, they actually form very beautiful patterns on the complex plane, very regular patterns that seem to somehow distribute very evenly. Okay, so what you're seeing there are actually a plot of the complex zeros of the Wronskian that I just showed you. And again, this is just for beauty purposes. I don't want to say much about them, although there are people, and I'm talking by Peter Miller and Roffelsen and Massoero. There's people that actually study using Riemann-Hilbert problems. They study the asymptotics and the distribution of the zeros. So there's some people that can tell you a lot about how these things actually behave. All right, so we are already halfway through the lecture. I can give you a small recap. And the recap is if you know classical polynomials, and they're like a nice chunk of cheese, well then exceptional polynomials are a chunk of cheese, but it has holes. Okay, so this is your take-home message. It's like one of these Gruyere cheese that have holes, but they only have a finite number of holes. So you still have an infinite amount of cheese. So still okay. All right, so I promised there would be a question in approximation theory. And the question is the following. Besides being interesting for mathematical theory, these things are interesting for their own sake. And besides being connecting to quantum mechanics, is there any application of exceptional polynomials in approximation theory? So can we use this instead of Legendre polynomials or instead of Chebyshev polynomials to approximate functions? Okay. Or otherwise speaking, what would be the kind of problem where you would rather use a basis of exceptional polynomial than a basis of classical polynomial? And I don't know much about it. I'm only going to give you an idea. But the idea is the following. So let's say you have a function defined on a finite interval, a and b. It can be any function. Okay, and you want to approximate this function with a basis of polynomials. But at the same time, you want to make sure that the function that approximates in that interval satisfies certain requirements on a number of points which lie outside the interval. Okay? So you want to both approximate the function inside the interval and make sure that the function vanishes, say, or satisfies certain requirements at a finite number of points that lie outside the interval. If that is your problem, then there's a very high chance that Jacobi polynomials are a better fit, because Jacobi polynomials automatically satisfy the extra constraints. They are built in to the definition. Okay, so you're approximating functions with things that already have this constraint by design, so to say. Okay. Now, if you're a physicist, maybe you're not that much interested about recurrence relations, so I think I will skip this part, and I will try to tell you something a little bit more interesting. So, well, you know that sort of classical polynomials satisfy recurrence relations of which are three-term recurrence relation. I will show you an example here. So normally, if you have a classical polynomial, you would multiply it by x, and the result you can write as a linear combination of Pn plus 1, Pn, and Pn minus 1. Okay, so that's a 3-term recurrence relation, and you need to multiply by x. Exceptional polynomials, you do not multiply by x. You multiply by something which is a higher degree polynomial in x, and it's precisely the primitive, or the integral of the weight denominator. Okay, and then you can also write it as a recurrence relation, except now you have more terms. Instead of being a 3-term recurrence relation, it will be 5 or 7, and so on. Okay, and this is just an example on how these things work. So the Jacobi matrix, which is what people call this matrix that encodes, if you want, the recurrence relation. In this case, instead of being 3 diagonal, it's 7 diagonal. But other than that, the theory works exactly the same. So it's an extension, if you want. It's a generalization of the classical theory. Let me tell you a little bit about bispectrality. Okay, I don't know if you've encountered this notion before, but it's an interesting notion. So now think about, normally you think about Hermite polynomials as being an infinite set of functions of one variable. So you think of the whole set of Hermite polynomials as being many functions of variable x. And I would like you to think about this now in a different way. So think it as a function of 2 variables, one discrete variable n and one continuous variable x. Okay, so now you're describing the whole set of Hermite polynomials as a single function of 2 variables n and x. Okay, and what can we say about this function of 2 variables? Well, if you define the shift operator, which is this delta f acting on the discrete variable, and you define your derivative operator, which is just the usual derivative acting on the x variable, it turns out that you can look at the recurrence relation as if it was a second-order difference equation, okay, in the variable x. Okay, so you write it like that, and that's precisely the recurrence relation that's satisfied by Hermite polynomials. And this x that you multiply h by, you can think more or less of x being the eigenvalue of a difference equation in n. Okay. Similarly, so that's what I just said. So you have a discrete operator with a curly t, a calligraphic t, acting on h of n and x, and the result is x times h. But you also have the ordinary differential equation, which you have there. That's Hermite differential equation. And the Hermite differential equation you can look as a differential operator acting on the same function, but now the eigenvalue is a function of n, not a function of x. Okay, so you see, n and x play a dual role here. Okay, and this means that you really have 2 spectral problems in 2 different variables, but your family of functions is an eigenfunction for the 2 spectral problems at the same time. Okay, and this is what people call bispectrality. Now, if you take this bispectrality and you start doing things, now look, typically at the beginning for Hermite polynomials, they are both order 2. So both of them are order 2. Now, if you do a Darboux transformation in the Jacobi matrix, it turns out that you maintain the degree of the difference equations, but you increase the order of the differential equation. And this thing has a name on the literature. They are called Kroll polynomials. If you haven't heard about them, don't worry, because it's a very specific thing. Now, what we're doing here is the opposite thing, is we are factoring the differential operator. So then the order of the recursion relation increases, and the other one stays in 2. So what we do on the discrete variable, on what we do on the continuous variable, they are kind of dual to each other. Okay, there's a notion of duality. And these things are actually called bispectral duals. And this is a structure that people exploit to derive results. Okay, again, this is maybe too mathematical for your taste, but I thought I would say. Okay, so let me tell you a little bit what these Darboux transformations are. Okay, so Darboux transformations, you start from your Hamiltonian, quantum Hamiltonian, and then you choose a finite number of what people call seed functions. Okay, so seed functions are just formal eigenfunctions of your Hamiltonian, but they have to be such that their log derivative is a rational function. Okay, this is important because otherwise you leave the algebraic class, the rational class. Okay, so you go from your Hamiltonian H to a new Hamiltonian hat H, where you add this new term, which is the second derivative of the log of the Wronskian, of the seed functions. Okay, and you can also transform the eigenfunctions from being the ordinary eigenfunctions of the harmonic oscillator to being that formula, hat phi n, which is the Wronskian of the seed function plus phi n divided by the Wronskian of the fume function. And this is called Cramp's formula, and it's a sequence of Darboux transformations. Okay, this is very well known. Now, normally you would have two types of seed functions. They're either called state deleting if the seed function is square integrable, as you see. So, and this we were going to signal now as going from a square to a bullet. This is a representation that I will explain to you in a second. But you also have state adding ones, and the state adding ones are the ones where the seed function is not square integrable. So that one it blows at infinity, and this will be the opposite transformation. So going from a bullet to an empty square. Okay. So let me tell you what Maya diagrams are, because Maya diagrams are a very easy pictorial way to describe the whole class of exceptional Hermite polynomials, and by extension of all exceptional polynomials. But let's stay to Hermite because they're the simplest case. Okay, so Maya diagrams are an infinite set where you have bullets and square. This would be the trivial Maya diagram you're seeing now. You put an origin, but now in order to have other Maya diagrams, you could do many things. So you add labels on both sides, and then you start throwing balls, and you take away some balls from the other side. Okay? So this would be a typical Maya diagram. Okay. Now, how would you label this Maya diagram? Well, you need to describe which are the new balls that I added, and which are the balls that I took away. Okay, so a convenient way would be give me the labels of the balls that I took away on the left and the balls that I added on the right. So once you give these labels, I can build this Maya diagram from the trivial one. Well, it turns out that this is the main result as far as classification goes, that for every Maya diagram, you can build a rational extension of the harmonic oscillator. And what the Maya diagram is encoding is precisely the set of Darboux transformations that you have to do on the harmonic oscillator to arrive at the exceptional Hermite polynomial. Okay, remember I told you that all exceptional polynomials are recovered by a finite sequence of Darboux transformations. Well, the labels of those Darboux transformations are precisely these little balls that I'm taking away and that I'm adding. And again, I don't have a lot of time to explain you this in greater detail, but this is the idea. Now, Maya diagrams are in one-to-one correspondence with partitions, okay, partitions of integers, and the correspondence is the following. So every time you see a bullet, I will go down, and every time you see an empty square, I will go to the right. Okay, so if I do that, first I go down, I go down, I go down. Now I have an empty space, I go to the right. And then I go down, down, right, right, down, right, down, down, and then it's all the way to the right. Okay, so when I write these three dots, an important thing about Maya diagrams is sufficiently far to the left, everything is bullets.
Professor,
and sufficiently far to the right.
There is a question in the chat box.
Okay.
No,
Question?
Someone has raised the hand. Can you raise your question now?
Yes, please, ask the questions.
Yeah, someone has raised the hand. I don't remember his name. Who has raised? Students?
I'm happy to.
Students, who has raised the hand?
Krishna Kumar.
Krishna Kumar, are you there?
Somebody raised his hand and disappeared.
Yeah. Krishnakumar? I don't know whether he has did it mistake. Okay, sorry.
Okay,
he's not
doesn't
answering.
matter.
Yeah, he's not answering.
I'm happy to answer any question. So do interrupt me, or otherwise we can save them from the end. Okay. Okay. Good.
Sorry.
So I was telling you how you build all this thing.
Yes.
This is correspondence, and this is very simple. And you see, after you do that, because now it's all the way to the right, and before it was all the way upwards, there appears a Young diagram of a partition. So that's the way in which you have a one-to-one correspondence between a Maya diagram and a partition. In this case, it's a partition 44311. Now, there's a notion of equivalence of Maya diagrams, okay? And that is the following. If I have the origin at that position, then this would be a Maya diagram, 52112. But I could move my origin, put it somewhere else. And now, of course, all the numbers are wrong. I need to relabel all those numbers because I'm moving the origin. Okay, so I do that. I relabel all my numbers. And then this Maya diagram, I could write as empty set, because there is no missing bullets on the left, and then 1, 2, 5, 7, 8. Okay. Now, if you don't think about the origin, these two Maya diagrams are perfectly equivalent. Okay, so there's a notion of equivalence. So 521 bar 12 is equivalent to the other one. But I could also move it to that place, relabel, and then write yet another one, which is also equivalent. And this would be 2, which is missing on the left, and 2, 4, 5, which are on the right. And you see the length of these descriptions might be different. It doesn't need to be the same. Okay, but they are all equivalent. So this is the notion of equivalence of Maya diagram. I will tell you why this notion is important. Okay, the next thing I want to do with Maya diagrams is I want to define a polynomial that we call a Hermite pseudo-Wronskian. And it's called a pseudo-Wronskian because it's almost like a Wronskian. I mean, look at it. It actually is a Wronskian. So the definition is the one that you see above on 24. Okay, but it's not immediately clear that when you do that Wronskian, you get a polynomial, because you need to take derivatives of polynomials times exponentials, and you need to, well, do the algebra. Now, this h and tilde, they are also Hermite polynomials, but evaluated at ix. I is the imaginary unit. Okay, so they are sometimes called a weak rotation. If you like physics people call this a weak rotation. Okay, now. So how do you build a Hermite pseudo-Wronskian from the Maya diagram? So for all the indices on the right, on the left, sorry, you write h2 tilde. So this is the 2 on the left, and you have to use the conjugate Hermite polynomials. And for 2, 4, 5, you write the ordinary Hermite polynomials. This is a determinant. I'm telling you how to fill in the determinant. Now, from the ones on the right, so 2, 4, 5, you take the ordinary derivatives. This would be the way you normally would complete a Wronskian. Okay, so every column in this case is just a further derivative of that object. But for the other funny ones, for the h2 tildes, instead of doing that, you increase the degree. Okay, so this is just you can show that this thing is the same as the formula in 24. And in a way, this is like a mixture of what people call a Casoratian determinant and a Wronskian determinant. Just a way to build something which is a polynomial. Okay, so take it as a definition. Now, remember the equivalence that I just showed you about Maya diagrams. So here you have 3 Maya diagrams that are equivalent. So they are the same. The only thing I'm doing is I'm changing the origin. And this would be the Maya diagrams in each of the cases. Okay. Now, for each of those Maya diagrams, I can construct a pseudo-Wronskian. And they're all equivalent, as I said. So these are the pseudo-Wronskian. And you see, the pseudo-Wronskians are determinants that have different size. The size of the determinant is precisely the number of elements in the Maya diagram description. Okay, so we have here size 4, size 2, and size 3. And do you want to guess what happens between these determinants? Well, they are actually proportional. to each other. So
Professor,
they're essentially the same.
Excuse me, Professor, there is a question.
Yes.
Ruby, can you raise your question now?
Yes, sir. Hello, sir.
Yes, go ahead.
Sir, I'm having a doubt in producing that pseudo Wronskians. So each time we are taking different combinations of between that H tilde and H. Oh, so for what reason, sir? So
there's different combinations of H tilde and H.
And H.
Yes. So, yeah, there's different combinations because I'm only reading what the Maya diagram says. So look, on the first Maya diagram, it's 1, 2, 3, 6. Okay, and these are the 4 bullets that I have on the right of the origin. Okay.
Yes, sir.
On the second Maya diagram, I only have 1 bullet to the right of the origin at position 2, and 1 empty bullet on the left on position 3. So you know how to build the Maya diagrams from the picture, right? Now the next thing is how to build the pseudo-Wronskian, and this is very simple. So whenever you find numbers to the right of the Maya diagram, like 1, 2, 3, 6, you write the ordinary H's. So H1, H2, H3, H6. And then you move to the right just by taking derivatives. Okay. When you have the mixed type, like you have the mixed type like 3 and 2, you need to write H tilde 3 and H2. So the information on the left of the bar in the Maya diagram are the tildes, and to the right are the no tildes. And then to complete the determinant, if you are on the right, you would take derivatives, and if you're on the left, you raise the degree. This is the prescription. And this, if you read the paper, you see that this actually has a reason why you do this thing this way. Okay? So I don't know whether I answered your question. This is how you build these things.
Yes, sir. So actually, how? So actually, just to understand Maya diagram, just to express the Maya diagram in terms of expressions, we want to do that Wronskian, sir? Pseudo Wronskians?
Yeah.
Okay, sir. Yes, sir.
The Maya diagrams are a pictorial way of describing the pseudo Wronskians.
Yes.
And what the equivalence is telling you is that actually all these polynomials, pseudo Wronskians, they are essentially the same up to a multiplication factor. So that is the main result. Okay, one of the main results that no matter how you build these determinants, if you actually put it in Mathematica or Maple, they will evaluate to the same polynomials up to a multiplicative factor. Okay.
So, and one more thing, that Wronskians is actually appearing in that function prefactor. These Wronskians have been appeared in a prefactor in the function. So does it represent all the combinations represent the same exception orthogonal polynomials, or?
Yes. So on the prefactor, let me see if I can go back to that slide. So you're asking about here,
yes,
right? So
yes,
the prefactor has the usual weight divided by a polynomial. Okay, and that polynomial is always the Wronskian. So when you define your exceptional Hermite family, you're fixing that Wronskian, 1, 2, 5, 6. Okay, and that you fix it and it appears as a denominator. It also appears on the weight, but it appears on the weight squared. Okay, so in this case, 1, 2, 5, 6, there would be a Maya diagram that describes that, and this is precisely a specific family of exceptional Hermite. Now, maybe you want to know whether any possible sequence will give you an exceptional Hermite, and the answer is not everyone. Okay, you need to choose them carefully so that you do not introduce singularities.
Okay,
but other than that, you have a lot of freedom to choose any family that you want. Okay?
Yes, sir. Yes, sir. Yes, sir. Thank you, sir.
Okay, I think we're almost over time. I have a lot
No
more
problem.
material.
Sorry, go ahead. No problem. Yeah.
Let's see. What do I want to tell you? Okay. Yeah. I was almost done. Okay. So we're here. Everything that I'm telling you about Hermite also applies to the Laguerre and to the Jacobi polynomials. Now, the Laguerre and Jacobi are a little bit more difficult because you have more different seed functions, you have more types of Maya diagrams, and it's a bit of a richer structure. But for a primer on exceptional polynomials, I think Hermite is more than enough. Okay, so these results we already saw, and actually by rescaling that factor, you can make sure that you have actually an identity. So you can have an identity between the two Wronskians upon displacement. Okay, this is one of the results. Now the next thing I wanted to tell you about, and now I'm going to switch to another presentation that I have somewhere here. Let me see. Okay, I'm going to tell you a different twist, and this is something that we only started looking at in the past couple of years. So it's the same story. It's still exceptional polynomials, except that it's a totally different story. Because now, because now you can have as many continuous parameters as you want. And it's actually a deformation, an isospectral deformation. So let me try to tell you what this thing means. Okay, and again, I'll start by giving an example. I think Professor Santilvalan was mentioning Legendre polynomials before. Okay, so this is an example of exceptional Legendre polynomials. Now, the normal P's that you find here, P1, P2, P3, P4, these are the ordinary Legendre polynomials. Okay, now if I modify them in this way, by actually adding certain polynomials multiplied by a continuous parameter, in this case, P4 is a real parameter. Okay, so I do this, and of course, I'm just showing you some polynomials. You don't know where these things come from, but believe me, it will happen that the new polynomials, okay, the P4 colon 0, 1, 2, 3, they are also exceptional. They are also orthogonal amongst each other. They will also satisfy a differential equation. So everything that I said before, it's still true, but now T4 is an arbitrary parameter that you're introducing. Okay, T4 can have any value within a given interval. Okay, now if you put T4 to 0, look what happens. If you put T4 to 0, all those brackets disappear, and then your polynomials become 1, Z, P2, P3, P4, P5. So you recover the classical Legendre polynomials. Okay, so what this thing is telling you is that this is actually a deformation. Deformation meaning when the formation parameter goes to 0, you are within the classical, and when you start turning the knob and changing your T4 parameter, the thing deforms. Okay, and it's quite interesting actually. I have a little video to show. Okay, so this is the deformation of the Legendre polynomials. So when t equals 0, you have the picture that you normally know. Let me try to stop it precisely at t equals 0. Well, not quite, but almost. Okay, this picture you've seen many times. This is almost the ordinary Legendre polynomials. Okay, but as t goes above and below 0, the whole thing changes. Oops, sorry. Okay, let me try to stop it somewhere else. Okay, sorry. Let me go back. Let me go back and try to stop it somewhere else. I'll stop it there. So you see the yellow polynomial that I'm showing here, it plays the role of the ground state. It's in the undeformed case, it would be a constant. This would be 1. But now you see it's not 1, it's never 0, but it's deformed. Okay, and likewise with all the other ones. So the whole Sturm-Liouville character still remains, and all these things will have the zeros that you are used to knowing, except that now the polynomials are different and they become deformed. Okay, and you can do this in many possible ways. So this is very interesting because it gives you many different models in quantum mechanics, okay, with lots of free parameters, okay. This would be how the orthogonality weight changes, okay. So the weight for the Legendre polynomials is 1. It's just a normal weight. But as you change your parameter, the weight changes a lot, okay. It becomes 1 precisely when it crosses 0, and otherwise it can have many different bumps, okay. And again, I don't have a lot of time to explain you this, but there's some recent papers. If you're interested, I can hand them over. This thing is not all that complicated. It's fairly simple. This is also perhaps an interesting example. Normally, if you look at the weights of all the classical polynomials and exceptional polynomials that were known before, the weights normally are either monotonous functions, so monotonously increasing or decreasing, or they are unimodal functions. They are functions that only have one maximum or one minimum, okay, like the Gaussian. But now we can create weights that can have more than one bump. Like here you have a bimodal weight, okay, and you can have things that are much more complicated like this. So I guess one of the interesting, I think I'm going to stop here. I will stop here. I had some things about machine learning, but I think that's a little bit too late. So I will stop here. Thank you for your attention, and I'm really open to whatever question that you might have. Thank you.
Okay. Thank you, Professor. Thank you. So now the forum is open for clarifications, discussions, questions. Yeah, Professor Kane, you can raise your question.
Yes. Thank you for your nice talk. I would like to know whether you have been able to do the same things for other orthogonal polynomials than what you have shown for the Legendre ones.
Yes, actually, Christian, it's really nice to see you. Haven't seen you for a while. All this thinking is inspired by a paper of yours and Eve. No, you and Eve did the first example of this what do you call confluent Darboux transformation.
Darboux, yes.
Yeah. So now we can do it. Now we are close to having a full classification. This is still work in progress, but we know how the game works, and we know how to iterate them, and we know how to mix them with the ordinary ones. But you can only do them, and this you know very well, on the Jacobi class when alpha and beta are integers. And the reason is because there's this degeneracy that you have the energy levels of the two sectors, they coalesce, okay? So we can do it. In Laguerre, you cannot really do it. I mean, they are very residual. I mean, introducing continuous parameters. If you want to introduce continuous parameters, you can only do it in the Jacobi class. And moreover, you can only do it in the Jacobi class precisely when alpha and beta are both integers. Otherwise, you cannot introduce new parameters. Yeah.
Thank you.
Christiane, by the way, was also, she made one of the most important discoveries at the beginning of all this theory. I should say that. I didn't do a historical perspective, but when we found this at the beginning, we found it almost by trial and error and trying new things. So we published the first example of these things back in 2008, I think. And Christiane, shortly after, she realized that those examples could actually be derived through Darboux transformations. So she was the one that actually gave the right tool to turn this into a consistent theory. In case you didn't know, now you know.
Thank you.
Yeah. Thank you very much for a very nice lecture. I would like to know whether Lamé polynomials come under this class.
Which
Can
one?
you have
Which polynomials?
Lamé polynomials?
No. Lamé are related to elliptic equations, so they are outside this scope. So when you look at exactly solvable quantum mechanical problems, Lamé would be when your potential is a Weierstrass P function, and then you are more in the realm of finite gap spectra. It's a different family. No, they don't fit in here. Now, an interesting question would be whether you could do something similar to this in the finite gap family, and you can, in fact. But we haven't explored that very much.
Yeah, the same question will come for Matthew functions because they will form a special case of it.
Yeah, that's also a good question. So Mathieu, yeah, we haven't looked at any of that. You see, because at the end, all we are doing is we are trying to do Darboux transformations of classical. So we stay within the hypergeometric class, and we try to transform these hypergeometric functions to preserve the rational character. So at the end, we are staying within a very restricted class of functions, polynomial rational functions. So all that you're asking lies beyond the scope, and we haven't looked at it. But it's a very interesting question.
Okay. Thanks.
I'm realizing that maybe I gave a very simple talk. I mean, there's lots of experts. Maybe I should have given more technical details.
No, sir. It will be useful to the students. They will get interested in this.
I thought it's better to keep things simple and get some key ideas, and then if somebody's interested, all the details are published.
Yeah. Okay, but I think students learned something now. Thank you. So, are there more questions? Students, you need some clarifications anywhere?
Well, for the students, let me say that there's a lot of interesting problems here. If you're just starting to work on mathematical physics, there are still open questions in all this theory. We have been working for the past almost 15 years and still consistently finding new problems. So in case you're interested, I'm happy to provide any further reference.
Maybe they're a bit hesitating. They will write to you. I don't know. Okay. I think there are no more questions. So I would like to conclude the session by thanking Professor David Gomez Ullate for accepting our invitation and giving a very wonderful talk on exceptional orthogonal polynomials. Thank you, Professor. Thank you very much for accepting our invitation.
Everybody, thank you for your attention.
It will be very helpful to the students.